maybe more things. Hey, anything you want me to know about homework 1? Was it everybody?
So, if we are choosing to implement like a change of basis, or sorry, coordinate system change, when we are getting like billboard coordinates, for example, in order to make the transformation work, we need that they are normalized. Otherwise, you can't just take the transpose of each of the vectors to make the matrix. You'd have to do some other decomposition stuff.
Homework 2, you can use the whole vector U from the that's one of the billboards. Here is probably a point that I met. I know that I didn't let you finish the question. I'll get in a second. Lower right, lower left, upper right. I can either treat this whole vector as a whole and now ask for P. Essentially, for me it was convenient to think about P as its x coordinate, so I'll represent P equal lower left, let's walk all the way to here, plus alpha times lower right minus lower left vector, and then alpha is translated almost immediately to a pixel. It's just between 0 and 1 rather than between minus and 1 and 1. So I still need to shift it a bit. And then I don't care at all how many columns I have on the billboard. And I'm not at P yet, I'm just here at P prime, the projection of P on the lower edge of the billboard, plus beta times upper right minus lower left. Upper, this left, yeah. Upper left and here, upper right. Yeah. And
so I guess my original question was, in the world, the big billboard may be very big. In local coordinates, our goal is to make it between 0 and 1 for getting the pixel from the image, or determining if it's on the billboard in the first place.
That was my recommendation, yes. It's not the only way.
Which means that to make the matrix conveniently, you need to normalize lower left to lower right, and upper left to lower left, right? Because if they're not orthonormal, you don't get the change of basis, or the matrix isn't convenient to construct, right?
When I can see a few different solutions. When I thought it, what was for me most convenient is to convert this alpha to be from 0 to 1. And now I know that there is an image of a house over here on this part, on this billboard, then alpha times, I still need to move alpha from minus 1 to 1, but ignoring this part, alpha times the number of pixels that I have to x, that gives me j, at which column I am. I is beta times ny, and while the colors that I need to report, my ray hits a billboard at point P, and the colors that I report is the color of the image at position input image at position ij. Again, just correct, yeah. And then I'm perfectly happy that alpha is between 0 and 1. The only potential bugs here is that I might get to index. No, I don't see any bugs here. Actually, I don't even need to worry about Florence Hill. When I get to Florence Hill, I might miss the very top pixel. So to be entirely fair, you want to think about each pixel. That, as before, that the pixel 00 is actually has a bit area, so you move it by half a pixel and then you're perfectly fine. Did I answer? And then I don't worry, but that's less mathematical. It's not exactly changing from one base to another.
You're just computing that alpha and beta using the vectors directly, rather than like a...
Or normalize it. I mean, I still use the normalized version B to compute the alpha and beta, if you want. I mean, the formula was called normalize and then all take alpha and divide by the number of pixels. You'll end up, or you should end up, like the same.
Thank you. For the theoretical questions, is there a specific place we should turn them in, or can we include them with our GitHub?
Include them with the rest, and if you have doubts and you want me to take a look at them earlier, yeah, then just make noises. So the idea was if I'll give it, we're a small class and I didn't apply everything that I applied last time. But if you want my feedback ASAP, just make noises and make it a priority. And then maybe it's even, and feel free to add it to the email again, if you want, just to see if the math is done properly. And for homework 1, that I think that everybody by now should have, almost everybody, yeah. Okay, eventually. Okay, well, back to classical, old, very slow graphics after the highlights of last meeting's NERFs presentation, which I'm debating if I'll ask you to actually do homework on NERF. I don't know if there is something that you can do on the basic. I don't want to assume that anything about which hardware you have access to, but I mean, you will definitely do GPU like WebGL, OpenGL homeworks, like homework 3, just homework 2, just fast. Okay, we talked about what we can get by taking a few images, for example, and average between them, which helps us create an object that moves together with the camera, and I move the camera by minuscule amount, much less than what is seen. Object that I want in the focus moves with the camera. Objects that I want to blur, like the out of focus, just don't move, so they averaged about it. It's a fancy way. You can get probably with convolution with Gaussian, the things that you don't want, maybe you can blur. Cooler image. I want to show the propeller of the, I think, Spitfire, I think. And how would you create it? You see the effect of the propeller moving as if it's a...
If you put like a ghost of the previous frame maybe on there for fast moving, or it's for things that change very rapidly between one frame and the other?
Yeah, we don't change the camera. We don't change the camera parameters. We do let the blade of the propeller be at a few different locations, and every pixel just average the results out of these 3-4 images, and what was moving is just looks smear. What was not moving is the same value in all the frames. So you get the very same value. Right, so that's essentially that's the image that you will see if your sensors have long exposure, so you're averaging the location of the camera, the location of the propeller, sorry, for a few different positions. Same idea, right? Average a few images. Now what's moving is balls, and take averaging of a few images. Same here, right? Want to create the fuzziness, the blurriness of the balls that does move and creates a feeling of where are they moving. Okay, and we are done with ray tracing array shooting. The middle for a single object. We are done with the three basic types of shadings, and we want to start speaking about triangular mesh and surfaces and interpolation. They are all put nice together, including how do we create shading on a triangulated mesh. So we will see different types of representation of surfaces that allows a designer to create shapes by controlling small amount of control points, like Bezier curve. You're moving points, and they become there is mathematical way like splines or Bezier curves or Bezier splines to create a curve out of it, and then we can move them in the third direction by making a surface of revolution. Just use this curve to create an axisymmetric shape, or move them in a different way. We'll talk about ways to create surfaces by controlling a very few points. That is how you can make your shape that you had in mind into geometric part. That comes later in the course in modeling. Right now, let's assume that I have a geometric object that came, say, from clear point cloud, came from with colors on each point. That is what NERSC tells us that a lot of these parts we humans should not worry about, and just let the neural network do the job for us. But standard graphics will say you have a triangular mesh, which is your shape consists of a lot, like very lots and lots of triangles that are connecting to each other, and each vertex in this triangular mesh has attributes associated with this, starting from where is this vertex in 3D, via what's the color of this vertex, via what's the reflectivity, transparency of this vertex, and so on. And out of it, we want to, together with camera parameters, we want to make a shape out of all of it. And to do all of it, we want to look at a triangle ABC and some point P inside this triangle. The slide will come back in a second, so don't rush to worry about. I want to look at a triangle and some arbitrary point inside this triangle, and I want to express this point P as a convex combination. Remember this term, we'll use it a lot. Convex combination of three weights. We'll give to each vertex a weight, how important or relevant it is for this point P, and then we'll call this weight a convex combination if they are all positive, and they will sum up to 100%. I ask what is the contribution to P? Maybe the contribution to the elevation of P. I want to create the 3 points live in 3 dimensions, and I want to create now a point on the triangle that they define that lives in 3 dimensions. Each one of the vertices will contribute something, and this something will be given by the weight that I'll give for this vertex. And we'll get back to elaborate on these slides, but to play with this a bit more, let's even, understand what the business of this weight in the simplest case, I just have 2 points, A and B. 2D or 3D, I don't care. And they have some attribute associated with them, say the color. The A is completely red, B is completely blue. And I want to create all the points along the segment, and along the segment, I also want to interpolate between these attributes, maybe the height, maybe the location, maybe the color. So how can I interpolate between them? And we have discussed this, I think, in this course, and even if not, you probably know what I'm going to say, but that's okay, let's repeat it. Okay. Here is A and B, and I want to decide the convex combination. The weight of A, the weight of B. It needs to be the convex combination, meaning both of them are positive, and they sum up to 1. And now every point C, or the point P over here, will be what? The weight that I give to A times A, the weight that I give to B times B, the coordinates of B, actually. That is the X times WA, the Y times WA, the Z times WA. And as I'm moving T, then when T will be 1, all the weight is given to A, which, because they sum up to 1, the weight of B must be 0. When T is 0 in this case, the weight of B is 1, the weight of A is 0. And when the weight is half-half, then voila, that's the weight is half. And I'll use it also to interpolate the color between them. Just use, that is, if you show me a point P on this segment, I'll compute what is the correct weights. What are the correct weights that create this point P? What are the weight of A? What is the weight of B? Which is just, in this case, just how much do I have? And that's interesting, that was actually writing it. So we would like to think that, again, P is the weight of A times A plus the weight of B times B. And it's tempting to think that if A is here, then the weight of A will be the length of this segment, D, divided by D prime, because it's a nearby segment to A, which looks perfectly reasonable, except that it's not true. But it's almost true. It's, how do I correct it?
The segment P to B.
It's the other segment. It's a segment that doesn't touch A. So it would be the double prime W of A would be the length of, would be the length D double prime divided by D prime, the length of the whole thing. And the weight of B is, of course, well, I can derive it by 1 minus, or I can just write. It is the weight of B is, where do we have it? Is the part that doesn't touch the segment. I have to 2D primes, so let's call it A. B would be D prime divided by L. And I can think about it in this way, or I can think about it, forgot parentheses. Don't do it at real time. So it's WB. I can write C in this way, but I can also write it in the following way. C, the very same C equals A. Think about A as a vector. Go from the origin all the way to A, and then go along the segment B minus A, the segment that goes from A to B, direction matters. Go along this segment. How much should you go along this segment? Well, if I want to make it all the way to B, then this coefficient must be 1. If I want to stay in A, this coefficient must be 0. And if in between, I'm just linearity. So it will be WB. Okay, so we can think about it as a few ways. Interpolate between 2 points, or make it all the way to A, and then continue, make it all the way to A, and then multiply WB by the vector that goes from A to B, this vector. Okay, and WA and WB are convex combinations. Remember it sums up to 1 and all positive. And by the way, had I let it be anything but a convex combination, okay. Let it be anything but a convex combination. For example, T equals 2, then C, I lost T. Here is P when WA and WB are WA and WB in this case they sum up to 1, but they are not positive. So
when you said over here WA equals D prime over length, shouldn't it be the other way around? Because we want WB to be 1 when we are at B, right?
So it's always the opposite part. WB is, look at the part that doesn't. That's why it's counterintuitive, and will be even more confusing when we move to triangles. It's the part that doesn't touch B. WB is the part that doesn't touch B. Because if I want all the way to be at B, then this part should be the whole segment. The part that doesn't touch B should take over. So it's also a way to find if a point lies on the segment or not when I know that it's on the line. All these terms create a convex combination. And so I am going to draw a bunch of points on the board. P1, P2, P3, dot, 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 to Pn. And I want to create the sum of wi's pi, wi's are all positive. The sum goes from I goes from 1 to n. wi's are all positive, and the sum of the weights is 1. So these are our two settings of convex combination. And so I have a bunch of points, 100 points. I am computing, I'm giving them all weights, and I require that the sum of weights will be positive. And I'm asking what is the shape that I create right here. And I'm asking somebody to please come to the board and draw the shapes that I'm creating. That is, it's a very intensive computationally. I check all the sets of W1, W2, all the sets of weights, and every time that I create such set of weights, I created a point somewhere on the whiteboard. And I want to know where are all these points. And while somebody is drawing it on the board, I'll do it in GeoGebra. Help yourself.
All the pairs of points will get you a line segment between them.
Mm-hmm.
There's a lot of combinations. Okay, I'm not going to do 2 to the however many combinations. But then each trio of points gets you a triangle. So this is formally called the convex hull. It's like what's the word, polygon? It's a polygon.
If the set of points is discrete, it's a polygon. It has straight edges. Some of the segments are on some of the segments that you created. Notice that it was only a convex combination, so how do I create a segment that connects 2 points? I just give non-zero weights to these 2 points and everything else is 0. That's how I create segments. And all in all, when I create all the combination of weights, what I create is indeed the convex file, defined as the smallest convex polygon that contains all the points, or commonly described as hold a rubber band around all these points and now let it snag. So you create this point. It was fast enough, so we don't need GeoGebra. So it could be that all the points are on the convex hull. It could be that the convex hull is just a segment. It could be that just a point.
Are we also including the interior of the convex hull or just the convex hull?
In this equation or in this description,
In this,
it includes every point inside it
Inside
can
as
be
well, right?
can be represented as at least one such convex combination. Okay, let's talk about barycentric coordinates. So again, I have the point P, and I want to represent P as A times WA plus B times WB. WAA plus WBB plus WCC, and I want to know what are the areas of what are the corresponding weights. And I'll start from interpolating the locations, but then I can use the weights to interpolate other attributes like colors. A is red, B is blue, C is green. By the way, in the previous GeoGebra, I was just setting the color of this point in the middle to be exactly WA and WB, because I can set the color to go exactly, and the weights were just determined by these two weights. The color was determined by the two weights. Okay, here, how can I find what are the weights? I remind you that when we had just 2 points, A and B, then the weight of B, for B, the weight of B was B divided by the total weight L. B prime divided by L. It's like the area of the portion that doesn't touch A. Now I have a triangle, and I want to compute the 3 different points. Think about the point P, it defines 3 sub-triangles inside the big triangle. Look at the area of each of these triangles. The area of each triangle corresponds to the length of this, the length of the corresponding segment. And I need to normalize it by computing the area of one of the sub-triangles divided by the area of the big triangle. Easy to confuse. I have 3 triangles. Which of them dominant when deciding about the weight of A? The same counterintuitive will work here. The triangle of A is a triangle that doesn't have as a vertex A. This triangle has A as a vertex, the same goes for this one. They are not corresponding to A directly. This that doesn't have A as a triangle, look at its area, the area of CB and this new point P, that is the edge that doesn't contain A divided by the area of the big triangle, that would be the weight of A. What would be the weight of C? Here is C, what out of these 3 triangles? The triangle that doesn't contain C, this one, the area of this guy, divided by area of Y to be, yeah.
So is it just like more computationally efficient to use the area formula, like Heron's formula or something? Or, because like why wouldn't you just like take a dot product to figure out what WA, WB, and WC are? Because
the dot product by each vector will, just projecting them in general will not work. I know it for sure because I convinced the students in the previous years that it does. It works only in the case that, and that can be used in the case of the billboard if you wish. In the case that the 2 edges are orthogonal, then it will work.
Oh.
But what is it? I didn't describe to the other people yet. I can also think about P as let's go to A and then let's go some direction in the direction of what? The vector that goes from A to C. That is, takes the vector C minus A, the vector from A to C, multiply by some constant. We'll see which constant it is. It's actually nothing but the weight of C, W of C. Similarly, multiply this vector, the weight of A, and you'll see the formula coming up. So it's again go to A plus go some amount in the direction of C, of this vector, plus go some amount in the direction of this vector. And now, once I have the 3 weights, I can interpolate between other features like, and it's used by the hardware all over the place. You need to, you're given location in 3D of a triangle, and I want to ask what is a triangular shape that is part of a plane that exactly fits through these 3 vertices. Well, we can just interpolate by using this amount, and by generating all these combination of W, A, B, C, we actually create all the pixels that stays in this triangle. That's how our hardware interpolate the location of triangle from location of vertices, because again, I can do it all in the ABC and interpolate height, for example, that's the attribute. Or in this GeoGebra, I just interpolate the color. And if you'll ask if GeoGebra will be kind enough, it doesn't, and I don't want to open, but the RGB that I set to this disk is just the weights of the three colors, the WA, WB, WC. Okay, so P is the weight of A times A, weight of B times B, weight of C times C. Can also be written as, in a very strange way, as weight of A plus weight of B plus weight of C times WB times B minus A plus WC B minus C. Right, because what do I have here? WB times minus A, and here I have WB times A, so it cancel each other. So this equals to this, okay? Because here I added WBA, WCA, but now I subtract WCA. WBA, WCA, so it cancels. But what do I know about this summation? It's convex combination, so it's 1. So I'm left with A. Again, it's not, I'm showing it because it's like different way to think about the barycentric coordinates. Go to A, and now you have two directions, and this tells you how much you weight each direction to go to this point B. And once you need it, you can have a formula that just spits out this area directly, what is a barycentric coordinate, or compute it from the area, or compute it by cross product, which also gives you the area. You have multiple ways to get to this value. And again, it's the area of the small triangle divided by the area of the larger triangle, except the cases that it's not. Right? It could be that everything here will work the same, except that it doesn't let me. Take P to be outside, and then the sum of the weight is just non-convex. It's negative or just don't sum up to 1. Again, for the intuition, why is this triangle that is the opposite? Notice that where P is right now, the color that I want to give to C is almost the color of the whole triangle, because P is extremely close to C, which is exactly what I'm getting. The area of this subtriangle of C is almost the whole area of the triangle in this case. And similarly to B. Similarly, what do I expect if P is on the edge? If P is on the edge, then what is the contribution of A when P is on the edge connecting B and C? Should be 0. Contribution of A right here is 0, so it's just contribution of B and C. And just linear interpolation, so it boils down to the case of the segment. And that's helpful because, in general, you'll have indeed the triangle with where you're interpolating attributes color between A, B, C, so you have some genome of, say, color along this edge. But you also have D, another triangle, that shares the very same edge. And since I'm interpolating only along these two vertices, then I don't get any discontinuity when I'm moving from this triangle to this triangle. Right? I'm not getting different answer from the interpolation of this triangle versus this triangle once I'm just interested in the common shared edge. Okay, so shading we are good with. Interpolation, it also tells us if a point lies inside the triangle. You can ask yourself, what goes wrong if the segments are not orthogonal to each other? Why can't I just project them? Everything works fine, but then the formula that I gave you for the billboard doesn't work. You cannot just project on each one of them independently because they are not orthogonal. But so it's alternative way to solve homework 2 and 3. And now we have surface, triangulated surface. Ignored at the moment how I represent it. Computer-wise, let's create a shading on this surface. I want to create shading of the surface, and remember shading has the ambient component, at which the direction of the viewer and the light are irrelevant, the diffuse, at which the direction of the light does matter, and I need the normal for the surface for it, and the specular that takes both direction of the surface and direction to the viewer into the game. Simplest and quickest. If all these polygons, all the triangles are small enough, then for each one of them compute its own normals. You have to have the normals if you want it to. Remember, if it's only ambient light, what do we see out of all this surface? It's only a disk that is uniformly blue. But we only can see the silhouette, actually, of the blue shading. The three-dimensional, completely depending on the shading. I need the normal to each surface, compute the normal on this triangle, and uniformly spread it on this triangle. That's the simplest, and it looks like crap, basically. It's very easy to see that what's the boundary of each triangle, because each triangle, presumably all the surface is taken from a sphere, but it looks anything but. And that's flat shading. Quickest, cheapest to compute, very obvious that something is working. Okay, and just remember the diffuse shading, we have the formula that takes the direction of the normal to the surface times the direction to the light. This cosine, this dot product between them. So we desperately need the normals to make it look less pixelized. And that would be like, what happens? How does it look if it's completely sphere? So we want to, we are using the first Guard shading, Guard model of shading. And Guard model of shading, together with Fong, that is the next one, they both of them need to say that's a simulation of an edge, E1. Here is an edge, E2. E1, it's normal to the edge. E2, this edge or triangle, the normal to it. And now I'll approximate the normal at this vertex to be just the average of these two normals. If I just sum them up, and it probably n takes the average, its length, of course, will be different. So I need to normalize it back to be a unit vector after that. But now on the plane, I just normalize two of them. Okay, and okay, the way to what do I do in 3D? So the shape that you see here is like two pyramids put on top of each other. They don't necessarily symmetric pyramid. I can move first one, and they both live in 3D. And you see a vertex T over here at the top that is adjacent to 6 triangles out there. So the idea is the same. Let's remove this triangle. Let's approximate the normal at the triangle by taking the normals to each one of the 6 triangles, sum them up, and divide by 6, of course, average them, and then make it a normal vector when you care about its length, unit length vector. Okay, just an example where I have multiple triangles that it's not always average by 2. In mesh, of course, the degree might be 3 or might be larger of each vertex. And Guard shading just says you compute the color based on all the shadings that we have, specular, diffuse, and ambient, of course. Compute the color of each one of the vertices, and now approximate using the barycentric coordinates, approximate along using the triangle. Right? So back to our pyramid, I can move Q on the point Q, and now I need inside this triangle to look at a 3 sub-triangle. Create a 3 sub-triangle. Each one has an area. I compute the barycentric coordinates of the area of the whole triangle of the mesh divided by the sub-triangle. I'm all in the business of computing the color at Q. All the business of computing the color at Q. How can I do? I compute the barycentric coordinates by computing the corresponding area of the sub-triangles divided by the area of this triangle, and now just use it to interpolate the colors at the vertices. That's Guard shading. And now comes the more confusing parts that will, and Guard shading is, well, if you look closely at the monitor, you can still see the boundaries between 2 vertices, between one triangle to each other, but at least it's more smooth because along a triangle you are moving continuously, gradually between the colors. Did I lose this slide? Yeah. The second improvement is Phong shading, which I don't know how to distinguish this Phong from the Blink Phong shading. Blink Phong shading that we used, that was a cosine to the power of an exponent to the direction of the light. So there are 2 Phong shading, and when I'll ask you in the exam, also I'll specify to which one. Yeah.
Blink Phong for specularity, or are you changing the width of the cosine?
Yeah. Diffuse, I know that the cosine is captures exactly the geometry. That's how area change. Specular has its own physics. That I read a bit about it, but far from being expert about why does it look so different. Why the specular shading looks so very different than just normal colors. And it has to do with the reflection versus particular light. And it's, by the way, I didn't mention it, if we have specular in water, then what happened to the rays that hit the water? What happened to the energy? Part of it obeys Snell laws and continues, and about 4%, that's the number that appears in the textbook, is the part that appears as specular shadow at all. And it behaves differently for polarized light versus non-polarized light. Yeah. So that was the first Phong model, to create something that looks like the physics model of specular light. And here is a second Phong surface interpolation that says something a bit clever. It says you want something that has very few triangles but still looks very smooth, then you need to compute, back to our triangle, stop it. So I need to compute for every point Q what is the color of Q. Q is one of the points inside its triangle. And for this, I want to interpolate not the color at the vertices. I don't have any special interest in the color of the vertices at all. The vertices, it's not the color of the vertex, well, not the shading effect at the vertices. I want to guesstimate what is a normal at the point Q. And I'm lying through my teeth out because I know exactly what is a normal to the triangle. All the points inside this triangle have an exact normal, which is 90 degrees to the surface of the triangle. I ignore it. I create my own normal. How? I'll look at the normal at T2. Remember, it was averaged of a bunch of things. I will look at the normal at, I'll show you the pyramids itself. So the pyramids, I have the point B. B was on the boundary of 4 triangles, this one, and 2 at the bottom. Average between them gave me this direction as approximation to the direction of the normal because of the effect of the nearby triangles. The same goes to this triangle. Remember, this is triangle of the model. This is one point on this triangulation. And now I use the barycentric coordinates not to interpolate between colors, but to interpolate between directions. I take this direction, which by themselves was approximation at the normal to the vertices, because there is no such thing as normal at the vertex, it's not smooth. Nevertheless, I started by approximating the normal to the vertices. That's common to both Guard and Fong. But Fong says inside each pixel interpolate these 3 directions. How? By giving the 3 vectors weights which are determined by the barycentric coordinates. Probably it will not be a unit length, but it will be a direction. And as we can expect, if I'm closer to T, then this normal is getting closer and closer to the direction at the normal at T. Closer to A, I'm closer to this direction. Closer to B, closer to this direction. Exactly what you'd expect. So makes sense? So, and that's how I compute the normals. So again, in 2D, it will just be compute the normals at each, the approximated normal, what you see in blue, and each of the colors. Again, this edge triangle has its own true normal. This edge has its true normal. Average between them, that's a blue. Average between them, that's a blue. And now for a point on the edge, use this formula that we saw earlier to give some weight to this normal, which is very close to this vertex. So it's almost 100%, plus some weight for the next normal. If it's triangle, I'm summing up 3 instead of 2. And as I'm walking along the edge, then of course the normals will move from being the approximated normal here to the approximated normal here, linearly interpolated between them. Let's say that I have big triangles. Which of the 2 methods, Guard versus Fong? If I want to create specular spots, which one have better chance to catch it? It's a classical exam question. I mean, possibly my surface is so well refined that they are both catching them. Possibly none of them catches it, but in general, without knowing what is the resolution. Which one? Yeah.
If you have a really large triangle, then would it make more sense to use Fong because, like, it would be more precise on like how the specular light should be interacting with the triangle.
Here is my surface. Very good. Here is my surface. So here are my normals, the exact normals. Approximated normal. Same here, approx normal. Viewer and I. Where do we have, what is the center of the specular spot? How do I know where is the center of the specular spot? Exactly where it's equal, when the incoming edge, incoming angle and leaving angle are equal, or exactly where you see where the eye and viewer, I'm good. Eye and sun. Exactly where the viewer sees the mirror, the sun, where this angle points to here. This angle equals to this angle, that's the center of the specular spot. And depending on your form constant, but good chance that you don't have any specular effect here, good chance that you don't have any specular effect here, which means that if you interpolate between 0 and 0, you still get 0 contribution of the specular, while Fong will say at some pixel in between, if pixels are dense enough, at some pixel in between, I have the normal not here nor here, but the normal just points, so direction to the normal and these triangles equal to each other. Okay. Let's talk about, and that can give you the illusion that even with very few triangles, it looks like it's a real sphere. Okay, reminder about about triangles, spheres, how we represent a sphere, plane, how we represent a plane, stuff that you also need in homework too, and following up homeworks. Okay, just summarization. And triangle, which you can represent as one vertex plus beta times plus b minus a, b and c in this case are the vertices, plus another wc, c minus a. Okay. And triangular mesh, how do we represent them in our computer, and how does standard standard format to triangular mesh looks like? So just slide to show you that triangular mesh are kind of important. Useful, very common way to represent surfaces. We discussed it already. When you see a triangle, and you want just based on the 3 vertices of the triangle to ask for triangle cooling, for example, can I ignore this triangle or not? It has 2 normals. I'll keep the agreement with myself that I'll look at the normal that I care for, the normal that the color represent to, is such that you are moving along the vertices in a counterclockwise direction. But if you see the 3 vertices and do the cross product, b minus a cross c minus a, if you're watching the triangle, so its face are pointing toward you. Why do you care? Because if its face are pointing to me, then and it's opaque, then there is another triangle that you see, but not the triangle that points to me. You care for the triangle that points to you. So you can ignore this one. Okay, look at this number, positive or negative. Negative, positive, it's counterclockwise, meaning that, remember, cross product, moving from b minus a to c minus a, which direction did this vector goes, and screwing it up, does it go in this direction? Okay, just the cross product once again. So you can decide about a triangle by itself, pointing toward or not. Forgot to mention, for the Phong interpolation, once we'll get to OpenGL or WebGL, and I'll allow you to use all the features, basically you are just saying which type of interpolation you want. And you're paying for it in running time, of course, but you're just saying Phong or Guard, and it's just a bit that you're specifying. Okay, now triangular, there are a lot of topologies that goes into what makes a good mesh of triangles. And I will not be very formal here, but I'll give examples of what will not be a good mesh. It should be something that locally looks like it's either planar, by triangle plus its few neighboring triangles. It's either planar, or that I can stretch it and put it nicely on the table, and then it will be planar and will not self-overlap roughly. So we cared about the vertices of the triangulated mesh. We care about edges of the triangles. Care about the topology and the geometry. Yeah.
So we had a slide just now that said how many vertices. Is each corner the number of vertices the total number of triangles that are touching it in data, or are we not repeating vertices?
Unrelated.
Okay.
We'll have an array that each vertex appears only once. But, in this case, there are 8 vertices. Okay, mesh topology, roughly speaking about who is neighboring of whom. How many triangles, which triangle is neighboring to which other triangles. It's related, if you wish, to planar graph embedding. A planar graph is an abstract creature that creates by vertices and edges, but I don't tell you how it is drawn on the plane, and an embedding of the graph. Okay, actually tells you. Now I rendered it, what's happening there. Okay, so we cared about the mesh topology, which now asks, are there any holes in the manifold? Hopefully not. Probably suggests that, right, because we want our manifold to be the skin of an object that has a clear interior and exterior. Just the same way that you'd say that this might be the boundary of a polygon, or this might be the boundary of a polygon, that you know for this polygon what is inside, what is outside, while it's harder to say if in this polygon there is a clear inside and outside. But the very same intuition should be all about triangular mesh. You should know what is inside and outside, and it gave some companies lots of money to actually create meshes that doesn't have a hole in the inside otherwise. And we studied in the hard way that send to CNC machine something that's supposed to be part of an engine and just produce the skin of the engine because of a hole in the interior and exterior. These questions actually are very well motivated. Okay, geometry, I just tell you where are the vertices, where are the edges, but I don't care very much about who is connected to whom, meaning that I can change the geometry without changing the neighboring relationship. And both cases, topology-wise, they doesn't have any holes, has to do with genius and has to do with Euler formula. Doesn't have any holes and defines created well skin of a single object. Okay, so we'll fix meshes with manifold, which locally looks like a planar. And we we'll try to avoid cases where I'll have too many points on an edge, too many points that are located at the same vertex, and so on. They're all good source of troubles. You'll see in a second what I mean. So, nice manifold vertex that lies on an edge, but if you're on an edge, there should be one triangle to your left, one triangle to your right. That's a part of a part, a portion of a part that we can manufacture. If you got this edge that is shared by three triangles, that's in 3D sounds fishy. Probably that's not what you're trying to manufacture, because the width of at least one of them should be 0. It's just a skin without. You cannot really fulfill everything into the surface. And probably it's good, and numerically it's good benefit not to have a vertex on 4 triangles, even though you can say it's 2 objects that just nicely share this vertex. But asking for some problems with stability of it and possible numerical analysis, and possibly when you manufacture it, produce it with 3D printing, good chance that it will become just the walls and will create a hole over there because of continuity. See, 4 triangles, too many triangles that shares a vertex, but they are not continuously making sense to share a vertex. Right? So try to avoid it. Definitely try to avoid obstacles that cross each other, at least. Not if you try to send it to a 3D printer. One triangle that penetrates into another one doesn't make sense as a skin of an object. Okay, and sometimes we relax boundary condition, that will be okay. This actually will be quite okay. I have a vertex that is shared by multiple triangles, and actually OpenGL are perfectly happy with such triangle strips, because in terms of representing it in your computer, it's enough that you tell it 1 triangle plus 1 vertex plus 1 vertex plus 1 vertex, and it will fill up the missing vertices, understand what's happening. But this is absolutely, that's still okay for us. That would be something that we'll prefer to avoid. But 2 triangles that are, two triangles, and it's not clear how this object continues in between. Doesn't look like a skin. And now you can ask higher, more interesting theoretical part. Right? We talked about what is the outside part. Outside for each triangle, it's a direction that you see the vertices in the right direction. And now it should mean that if I'm walking along this edge, it's nice because now I'm walking along this edge, the edge from A to C. If I'm walking along this triangle or walking along the neighboring triangle, I'm crossing the edge, either case, in opposite direction, which is kind of, but the edge itself is, per each triangle, the edge is crossed in a counterclockwise order. And I would like to make it now boundaries of a reasonable shape. I would like all these triangles to be consistent with each other. So the outer sides, you told me, well, you said based on one triangle, I should be able to tell you which direction is the outside, it points to the outside of the shape, which side is the inner one based on the cross product, the ones that you see the 3 vertices. In a counterclockwise, look at the cross product at the outside, which means that if I'm moving from this triangle, the correct side, to its neighbor, I am still on the outside, and so on. And I should continue, and it all makes fine in this case, and doesn't make sense in the very famous, you'll know it, very famous Möbius strip. That is exactly the example of what goes wrong with a Möbius strip. It cannot be the skin of a, it cannot be strips that I cut from a larger part, and that's the outer and inner strip. Okay, now how do I represent it in my computer to do reasonable calculation? And I would like to do queries like send it, of course, to the graphical device, one triangle, but I'll also need to ask who is a neighboring triangle? Who are the triangles that are all shared a vertex? Anything that will help me move from one triangle to the neighboring one. So here is the first object, the first attempt. We will have a triangle as, I'll tell you what are the three vertices, the location, X, Y, Z, color, color, RGB in each one, maybe color with respect to each shading. I can fake normals. Why would I want to fake normals? Because I want Phong, going back to Phong interpolation. I want, the triangle by itself doesn't know what is approximated normal the triangle. It's up to us to tell it. And for this, we need to compute what are the neighboring triangles. Okay, so we can have each triangle stores the three vertices explicitly. We could, it's a bad idea, that each triangle will tell us what are the X, Y, Z of the three vertices. And it's bad for multiple reasons. There are probably more than the ones that I thought of. So one would be that the description of a vertex is a long float to start with. And you have X, Y, Z, and you have the color. The vertex has a lot of data in it. Now, look at the vertex B. It appears in three triangles. In the example with this pyramid that I created earlier, I had vertices with degree 6. One vertex that lies on 6 different triangles, meaning that I double my data by 6 times. But memory now is cheap. Ignore, even if the memory is something that we can ignore, concurrency issue. You modified something in geometry, you need to make sure that no other process access all the vertices, because maybe you changed some of them, but you didn't get enough to change the other ones, and you are in troubles based on this point. Now, let's say that I represented each vertex, I represent the x coordinate of a vertex as third, by 3, 3, 3, and now I'll scale it all by multiplied by 3, scale it up by multiplied by 3, and it's quite likely that one of the vertices will be stored as 0.999, and the other one will be stored as 1, which now implies that what you thought are these three triangles that forms a nice scheme, suddenly you created either a hole or two triangles that overlap in between, and it doesn't look like a skin or surface anymore. So what are we doing instead? To start with, we will have one array of the vertices, array of all the vertices from 1 till n, and every vertex appears on this array only once. Now, it's not that the first option is completely useless, it's in a sense the quickest, but it's a risk that you have to take. Option 2 would be, here is an array of vertices, where a vertex 1 appears with its x, y, z, plus any other attributes, normals, colors, and so on. And what is a triangle now? Triangle will consist of 3 integers, which are what? The indices, or think about it as pointers to the array of vertices. So now I store the triangle only has 3 integers that tells me vector that this triangle has vertex 0, vertex 4, and vertex 1 of each triangle. And that starts to be okay. Now, so the next we'll talk a bit about data structures that can help us move from for example, I want to compute the approximated normal. What I have is, from a triangle, I know what is a vertex. But how do I know what is a neighboring vertex? If I want to approximate the normal, I need to talk of the triangle next to a vertex. And so far, the only algorithm that we have is, I want to know who are, going back a slide, I want to know what are the other triangles that share this vertex. I need to scan the whole area of all the billions of triangles to ask, is vertex B appears in any of them? So that's, we'll have a cute data structure that can handle this type of queries, as well as moving from one triangle to the neighborhood to the next one easy. And the key observation there would be that instead of having an edge A, B, one edge from A to B, we will have two edges. Each one will be what we call the half edge. One that goes from B to A, another half edge that goes from A to B. And these two edges can point to each other, and each edge knows at which triangle it lies. And this way I can move from one triangle to another, and I can make it in a way that go around a vertex quickly. And there will be, we have later in the course a whole section about other data structures like quad trees, R trees, locality sensitive hashing, so on, that can help us handle much larger scenes. Binary space partition, obviously, there is, yeah. Including painter algorithms that answers a bit what we described last time of scanning, of drawing from forward to backward. Thank you.
Is it the deco structure or just or this thing to do the current?
There is plenty.
DCL or is it some other?
DCL is a bit overkilling because if it's only triangles,
So
doubly connected edge list. There is a wedge data structure that tries to do it, and wings data structure with very minor differences between them. DCL will work, except that if I know that, if I ignore the outer face, then everything else is a triangle, so I don't have to have it. But it's minor details. So DCL is, the idea of DCL is exactly this.
Okay, thank you.
Thanks. What do I do?